I think I need to, because I received the message, this meeting is being recorded. Got it. Okay. Hello, everyone. This is an absolute honor today to present my ongoing research that I'm involved in CircuitPath project. Actually, today I'm going to present for actually our recent framework for structural health monitoring. And so we'll start with the wireless sensing that we developed and also to the frameworks. I'm actually doing my PhD under the supervision of Professor Francesco Freddi in University of Parma. And I think, okay. Just a little bit about myself. I took my bachelor in Iran in 2019, and then I in civil engineering, and then in structural engineering. I did my master again in Iran in 2021, and from the beginning I was mainly focused on structural health monitoring. Then for my PhD to operational model analysis, and recently I'm also working on the integration of AI, the machine learning methods with OMA and SHM. Just a little bit about this, the project. CircuitPath is the European Union project that I'm in. We are 10 PhD students. We have contributors from IFAG in France, Granada in Spain, University of Stellenbosch in South Africa, ENTP in France, Parma in Italy, and Braunschweig in Germany. The goal of the structure is to develop a smart, sustainable, and digitally connected pavement. And I started the project in 2023, 16 April, and we'll finish in 16 April 2026. So it's kind of to the end. And what I'm doing in this project is the topic is dynamic interactive digital monitoring system for bridge management, which we focus on three main goals. We try to enable a network of intelligent sensors sensing system for structural monitoring. We try to guarantee the structural safety with this network, and then we try to develop models and protocols, softwares for real-time bridge monitoring. And my project is integrated in between like two sides. One side is field instrumentation, and the other side is data driven analysis. Well, just a quick recap. I'm pretty sure most of you know, but we have two approaches for identification of modal parameters of the structure. One of them is EMA, experimental model analysis, and the other one is OMA, which the main difference is in the input excitation to the structure. For EMA, there is a controlled excitation that we impose to the structure, then we record the responses. But for OMA, we can monitor the structure under actually operation. That's the benefits. So we no more need to, for example, for bridge cases, we no more need to actually cancel the traffic. We can monitor it, and we assume the input as white noise. We assume the input as like some random stochastic input forces. And actually, we are assuming three main points in OMA, which as I said, we assume white noise as an input excitation. Then the excitation and the structural response are uncorrelated, that we can find the actually relation, and the structure doesn't change so much during the monitoring. And so there are two main approaches for OMA. We have frequency domain methodology, which is, of course, as it comes from its name, there is an analysis of the frequency content of the structural response, and time domain, which is actually considering the analysis of the response in time domain. And of course, you know that we have two main types of monitoring, which is wired and wireless. Each has its own pros and cons, but for our purpose, which is OMA, it's much better for us to use actually wireless because they are like flexible, they're easy to install. In the cases that we need some roving sensors, that we need some different setup, we can easily manage to have it. But there are some challenges for our wireless. One of them is the battery powered, which is like the source, the energy source is very important for us. And then the data transfer should be careful. And the third one is the data synchronization, because we are recording data wirelessly, so we need to synchronize to be sure. For example, modal parameters, we need to be sure, for example, for mode shapes, we need to actually be certain about the synchronization. Now let's go to the proposed framework that we had. From the beginning of the project, I was cooperating with Fiamma. With the R&D department of Fiamma, is a factory located in Parma, in Italy. We have proposed a system consists of three main components. It has wireless sensors, a router, and a cloud platform, which are connected to each other. Actually, as you can see here, there is a set of configuration that can be set by the users, by different users actually. And cloud is responsible for the connection, for bridging between the router, which actually get the data from the sensors, and then sending the data to the users and also receiving the configuration, which I will get deep into it later. So these are the three main components. These three pictures are just for the GUI that we have developed. We have developed a actually graphical user interface, web-based, so that we can connect the sensors with the users. As you can see here, for example, you can see each of the sensors with their address. This is just for an example. We can set the sampling start time. We can set the sampling interval between the different recordings. We can set the length of each recording, and then we can set the sampling frequency. Here we can see that there is an information for each sensor, which is if it is active or deactivated. What about, for example, the temperature that is recording, about the battery voltage, and also about the coverage of the network, because there is a router connected to the sensor, so we need to be sure that they are connected. And the third one is the results of the recording for each set of recording. So that you can, for example, the user can download the CSV file, they can plot them there. And so this makes it very easy for the connection between the users and the sensors for sending configuration and receiving data. And then the important thing for this setup is we actually considered it as a cost-effective and power-efficient. Now I'm talking about being power-efficient. What do I mean is we have an awakening workflow for the sensors, which they're mostly in sleep mode unless we trigger them, and then they start recording by the specific configuration that we have set before for them. So they're mostly in sleep mode unless we actually trigger them via the cloud command, the cloud router command by the users, and also by the scheduled start time that we have actually specified before. And then the system initialized. So it initialized the sensors, initialized the storage, initialized the actually power internal module, and then it loads the configuration that we have defined for it, and then synchronization. So the timing is now set, and then the data is started to be acquired, recorded, and then there is an upload and finalization, and subsequently it goes again for sleep mode, which saves power. Let's go to specifically to the sensors. Actually, we use MEMS accelerometers, ADXL 355, due to its internal ADC converter rather than 354. We use MEMS because of these four important things. First, it is low power consumption. There are like high sensitivity. They have high sensitivity and affordability. And this is the PCB that we have inside a box, the printed circuit board inside the box. The box of our sensors consists of an antenna, which is either connected to the box or is connected via a short, like a meter and a half wired antennas to, for example, the barrier on the bridge. We can connect them, and it has a battery. And then the sensor itself, it composes of an oscillator, which is responsible for the time, for the timing, time setting, the microcontroller, which is the heart, the brain of the actual PCB, and then the MEMS accelerometers, the wireless communicator module, which is responsible for the communication, and then we have two 8 megabyte actually memory for it to record the data and send. And then these are the key performance specifications of the system, which we have the ability to set within this sensing system from 62.5 hertz, the sampling rate, to 500 hertz. this synchronization for us is less than 2 milliseconds, and we have actually developed a small algorithm to like synchronize better. It's in the paper. If you want, I can give you the paper detail to read later. And then the sensor is able to record in 3D, and with plus minus 2G as the range of the recording. And then there is an outdoor Wi-Fi range covering 150 meters approximately. So this means that if you put, for example, the router in the middle of the actually bridge, we can cover around 300 meters by that router, which is actually the coverage. And then the operational lifetime due to this battery and their design is 5 years. So each 5 year, the battery should be like change. Yes.
This Mercury network is a doctoral network.
Yes.
And of course here, I think it makes sense to have hardware that have the research, but a lot of this is done also by companies. We have a company, a spin-off of the Bruce Wilmos, that develops these kinds of solutions,
yes,
packaging, mostly with cable sensors.
Yes.
Is this suggestion because you feel like there is no company offering this solution right now?
Well, actually, it's due to the 2 points I mentioned. We try to make it like very accessible with the commercial components, and also we try to like make it power actually efficient to develop the later things which I will explain. So this was just like a base on doing.
What I'm saying,
yeah, I completely understand.
Solution.
Yes, they are in the project actually. So they are the contributors of the project, something like this. So for the verification of the proposed system, we use just like this simple for a storage here aluminum structure, and we applied operational model analysis both in frequency and time domain, and also the configuration different sampling rate from 62.5 to 500 to 256 with like 15 minutes to 1 hour. And then there were like tests were done under the external conditions, so no input excitation was actually imposed to the structure. It was like just like natural excitation. And so we use also the shaking table, which it's not it takes so much time if I want to explain, so I just like wrap it up so quickly. So this is the shaking table which is here for the validation of the precision of the sensors, and then we validated via the FE models also. So now I'll show you the result of OMA here. As you can see, this is we have mounted one sensor in the middle of each of the actually floors, and then with the natural excitation, these are the result. As you can see, there's a combination of a stabilization diagram actually estimated via the time domain method, stochastic subspace identification, and also the PSD of the frequency domain decomposition. So we have estimated the natural frequencies, and we have validated this, also the mode shapes, and we have validated this with the FEM models. And as you can see on the right side, you can see the model assurance criterion, which shows the similarity. It's a matrix that shows the similarity between the time and frequency domain. As you can see here on the diagonal, values are close to each other, which means that it is like a cross-validation between time and frequency domain methods. Then we actually implemented this network, this sensing system into a real case scenario. It's a bridge in Parma province. Its name is Lamberty. And so this bridge is a concrete arc bridge. It's built in 1933, and it has 3 spans. Each of the spans length is 38 meters, and the total length is 114. So as you can see here, we used like one single setup because we want to be sure about synchronization first. So we used 30 sensors at the same time on this bridge. So as you can see, there are 2 joints here, which we use to actually a set of sensors beside 2 joints, and each of them is the rest of them has the distance of 9.5 meters. We used duration of recording of 1 hour. And the sampling rate for us we tested with 125 hertz and 62.5, and we use a solar panel for like for actually as a battery source of the rotor here. And so this is X, Y, and Z, because for the mode shape this was important. And these are, as you can see, the pictures that we mounted the sensors on two sides of the bridge. Here you can see the results of SSI covariance-based and frequency, I think enhanced frequency domain decomposition we use here. And then these are the model properties of the results of model parameters of the structure. This is the first mode with three methods, so time, frequency, and frequency domain. The second, and then to the seventh mode shapes. Just the intention behind this was just to validate the structure, the proposed monitoring system with the real case, and this is the map for the 7 modes for the time and frequency domain. From here, I want to explain actually the proposed framework that we have developed. We had 4 motivations for this, so 4 challenges to address. First, I'm pretty sure that you know that after the extraction of model parameters from the structures, we considered any deviation from this healthy base as damage. But the problem is that there are external environmental and operational factors which affects these model parameters kind of sometimes intensely, and we cannot misunderstand this. We cannot misclassify this as damage, and it's very important. According to Professor Brinker book, he said 5% of variation daily and 10% seasonal is to the model parameters. So this was the first concern, that this framework should address this. The second one was SHM is an interdependent task. So each of the module that we define for the framework should be connected to each other and should have a follow-up like progression. This was the goal. So we shouldn't behave it as an isolated way, just like to model identification. We need to connect model identification to damage detection. The third one was to condition the environmental factors with AI and to implement actually the AI methodology, machine learning models. And 4 was to make this an automated process so that it is first easier to implement for the people with the least knowledge of SHM, and also it's much faster, and it could be the base for real-time monitoring later. There are 3 main questions to respond. First, how the structure behave, model identification, when there's a first alarm, health assessment, and where and how much is the problem, which is the damage localization and severity estimation. So we have 5 actually consecutive most important steps. We have data acquisition, data pre-processing, model identification, health monitoring automation, and damage localization. And we try to automate this process in our 3 modules that I will explain later. So we're going to have we're going to integrate that. So let's go first for model identification, this first one. Let's go for this model identification, which is also embedded with this data pre-processing. What we did is we used SSI covariance space. So it's as I said, it's a methodology in time domain. As you know, the result of SSI is the stabilization diagram, right? And then it creates some poles of which each of them encapsulate the dynamic behavior of the structure. If through the order of the stabilization diagram, as you can see here, if any pole is repeated constantly and in a constant manner, we consider that as a stable pole of the structure. But the goal for us was to automate this process. So the result of SSI is a set of physical modes which appear constantly and noise produced unstable. After that, what we did was we need to define a band search for each frequency, for each natural frequency, right? To search for that band automatically. And so there are 2 things to put into consideration. First is we need a search band, and then we need a search tool. For the search band, what we did was we defined an adaptive frequency band, which first, before doing anything, we actually estimate the approximation position that we expect from the location of natural frequencies through FEM models. Then what we did was we expand this band with the perturbation progressively from 5% to 50%. So we search for the position of a stable pole starting from 5% to 50%. Dynamically, and the first perturbation that the model is successful to find a stable pole it stops. Why we are doing this? Because through environmental factors, the position of natural frequency changes, or if we have damages. So we have to be sure that we cover them. And from the other side, we have to be sure that sometimes the modes of the structure are closely spaced. So they're very close to each other.
But can I ask you, in real objects, we hardly ever have a really reliable finite element model. And oftentimes, the real frequencies are not very close. Do you need this as a step to start from that?
We need an approximation at least, because we need to define a frequency band. Yes.
But why would you think this? A standard SSI code method does not require this, and there are other methods for.
Yeah, but in the end, you need to choose it manually. You need to choose the stable pole manually. There are
codes already implemented in software such as MASEC for automating stabilization analysis.
I've also seen in Artemis, there are methodology for that.
That's my point. So you don't need to be tied, to the estimation of the finite element model.
Yes, but when I actually use Artemis for some projects, it sometimes randomly choose the poles if there are like noisy data and.
Can do some sorting a posteriori, but that's not so much, it can be based on your expectations, but I don't see why you need to limit yourself by starting from that limiting assumption, which is the FE based. Why not do it automatically and then see what modes make sense?
That also makes sense, but this is an approach, I think, in this case, it's also possible. With this searching band, so we need to actually find. So the moment it finds the first pole, it stops, and it does this for all of the modes. For searching for this search tool, which I mentioned here, we first estimate the stability score stability score for each group of poles, which first we round them, then we divide the number of stable occurrence over the number of orders to find which of them is stable, and then we actually use these Gaussian mixture models by defining two like k equal 2, which is like two Gaussian actually distribution. We'll find the stable pole here. So we choose two of them, and the one with the high mean, we actually considered that as the stable cluster, and then the highest score inside that shows the stable pole. And then we actually determine the dominant mode shape, because as you know, each mode also encapsulates, if we record in 3D, we have three types of eigenvalues. And then we actually estimate the contribution of those three to see which one is dominant. So we call them the modes bending, like axial or lateral, something like this. And this is the GUI that we practically use to actually implement this methodology. So the user can just browse the data which is received from the CSV file that we had with our system, and then it should specifically actually choose the maximum order and the block rows, and then the specific filtering that it desire, and then detrending, and it finds the mode shapes and also choose the dominant actual mode type and all the natural frequency under types. And here you can also see the stable pole estimation that it shows with search within a perturbation. For the next one, for the existence of damage, as you know, as I mentioned, the temperature, humidity, and operational loads can mask actually the damage. And natural frequency are a good tool here to just determine if there is something happening inside the structure or not. So we need to actually establish a baseline for the healthy behavior of this structure, and for this healthy baseline, we need a set of healthy measurements from the structure under different variation of external effects, and then we need to, after that, we pass them through the first module, and then we calculate the natural frequency for the healthy structure. Of course, they're varied due to the external effects. And what we do is we then developed a autoencoder ANN here to be trained on the healthy natural frequency to reconstruct them. Of course, they're varied, but the reconstruction error matters to us. So we can define a damage index as the global reconstruction error for these natural frequencies in the end. And then we can classify the health of the structure into four different states, as we have the healthy I also have to mention this here, that we also have employed this thresholding here for the reconstruction error, the progressive thresholding, which in the beginning we consider 90th percentile of the healthy MAE or MAPE, whatever reconstruction error as the healthy, and then we define. Actually, we then find the average of that with the least reconstruction error for the damage scenarios to find like a threshold for damages. And this is the implementation on that of that. So you can put the first 6 natural frequency, and then you can see the reconstruction error. And based on that, it will say if the structure seems to be healthy, or it can classify the health of the structure. The third one is localization, and severity estimation. So as you know, mode shapes and modal curvature, their second derivative, are extremely sensitive to noise and also require dense deployment of sensing system. So we use actually a time series data driven here to capture the behavior of the sensors through progressions. What we did was first we record the healthy data of the acceleration data through different data acquisition like series under different environmental and operational conditions. And then we applied pre-processing. So we did data logging, we did the truncation to be sure that they have the same length, and then we applied discrete Veillet transform to decompose each signal into some detail and approximation coefficients. As you know, approximation coefficients isolates the content of the signal in low frequency and detail in high frequency. So after a set of level decomposition, if you consider the approximation coefficient of the last actually layer, we can consider that as the trend of the structure, as the behavior of the structure in low frequencies, the pure behavior, dynamic behavior. So any variation here is obvious that they've also reduced the noises in this case. Then we actually extract and store the approximation coefficients for each sensor through the data sets. And in this case, if we train a model on this, we'll train a model on we will have a special temporal signature of the healthy basis structure. And for this purpose, actually before training, we applied the window averaging of the approximation coefficient. And we had 2 reasons for this. First, we want to just actually remove all of the outliers, some weird outliers if we have, so the noise reduction. And we need to reduce a dimension for the upcoming AI modeling. Afterward, there's also actually optimization for this window. That's we reconstruct the AI model, whatever we have the least error, we choose that as the best window. And then we developed, and then we actually assembled 3 input matrices. So we will have for the behavior of the structure in an X direction, we have a 3D matrix for Y direction and for Z direction, and each of them is like this. So the rows are the test sessions, the columns are the time series, and this is the number of sensors, the feature, the third dimension here. And then we developed AELSTM, the large short-term memory models, 1 per axis. So in the end, we will have three actually models. So we will have samples, time step, and features, and the reconstruction will show the discrepancy of each sensor's behavior. So afterward, this is important to say that this module is only activated when we are sure that there is a damage, right? After the module 2, verify that there is a damage. And then for any new data, we do the same processing. We apply detrending, truncation, DWT, windowing, and then the tensor formation that we have. And we construct the reconstruction. We actually estimate the reconstruction errors. So we had, in a scenario that I will explain later, if we have, for example, a set of sensors on a simple beam or on a bridge, we assume we actually consider some zones between each adjacent sensors as the discrepancy, as the subtraction of the absolute reconstruction error between 2 adjacent sensors. And this is done by actually calculating this reconstruction error, the subtraction of the reconstruction error between two adjacent sensors. And this is if you want to implement it in GUI, but I will explain the validation of the laboratory structure later. So here you have to just actually browse your X, Y, and Z data sets, CSV files, and then it automatically calculates the actually damage localization. And as you can see, it shows both, I mean, all in three directions. And also you can see here in another plot. For the validation, we need to replicate the real behavior of this of the bridge cases. What we did was we considered a laboratory structure with some interconnected steel box beams. The structure features three joints to replicate the real bridge, and it is secured. Each of these joints are secured with two plates, as you can see here. Each of them has 8 bolts. So in total, we have 16 bolts for each of the connections. Why we did that? Because in the end, we can easily reduce the torque values for damage simulation, for applying damage simulation. It is equipped with 10 three-dimensional sensors. The recording actually is done without the input excitation by us. It is done because the bridge was positioned outside of the factory, so there were cars passing by of the street. So we had like some passing vehicles, vibrations, and then we have some nearby factory machinery. But we were very careful not to create some repetitive actually inputs, which is not good for OMA, and other natural environmental effects, which like wind, we had. We recorded the data every hour for 13 minutes, for 30 minutes, sorry, every 2 hours for 30 minutes. And then with 250 different tests, we repeated this 250 times, and each of them was 250 hertz. Why we choose that? Because the maximum desired natural frequency was located around 42 hertz. So we were sure that with an Nyquist frequency, we cover what we want. And the temperature during the recording was varied between 15 to 50 degree. And the humidity also varied 54 to 83. So we covered different operational effects and different environmental effects. And we were just curious to find the correlation between them and how they affect the natural behavior of healthy structure. And also we have applied 3 damage scenarios. In the first damage scenario, we just applied 45% reduction to the torque values of the left connection. For the second, we applied on both sides, but the right one also 30%. And in the third damage scenario, we applied in 3 points of the structure. In addition, we have also 10% in the middle. We try to have it like a fixed and repeatable damage state. So after each reduction, we were sure that the total behavior of the structure doesn't go like in a strange way. So we also controlled other connections, and the damage scenario will completely in random natural environmental and operational factors. So these are the estimated natural frequencies through the first module that I mentioned. As you can see, through 250 different tests, these are the first 6 natural frequency of the structure, and these are the mean, max, and the variation. So we can say that the frequency variation across the tests were around like 5%, so 3 to 5% as expected. And mode 5 and 6 shows slightly a little like spread, specifically mode 4. And this is the result of the second module. We trained the AE model on the healthy natural frequencies, and this is also the actual estimation of the thresholding, which I mentioned earlier. And these are the health classification of the 3 damage scenario. This is first damage scenario. As you can see, we have for each 6 mode, we have estimated the mode type, and then the internal natural frequency and the reconstructed error, and the overall, and then estimation of the classification. And this is the localization for the 3 scenario. The first, as I mentioned, was just on the left on Z2, which was the connection here, which was between sensor number 2 and sensor number 3. And this is the cumulative bar chart for the localization of the damage. As you can see, for all 3, it was successful to find and localize the damage. But there were key areas that we intended to develop from the current framework that we had. First is we had time domain methodology. We tried to incorporate and couple that with also frequency domain. So in this case, we estimate the model behavior of the structure with two different ways. They're not different, but one of is time, one of is frequency. In the end, you can do a cross validation between them. And the second one was this time we wanted to. Previously, we implicitly covered the external effect. This time we want to explicitly condition the AI models with the M models, and this is why we use conditional variational autoencoder that I will explain later. And third, we chose and actually we relied just on modal certainty. So we said that modal parameters natural frequency varied, so there is damage. But here, beside the modal parameter changes, we verified with a second verification in time series, which I explain later. And also, this time we used 500 different tests. So we increased the tests double. This is the total framework, as I mentioned. So again, we have 3 modules, but different actually specification. For the first one, as I mentioned before, we calculate SSI. We actually apply SSI and we calculate some poles. This time, we also implement FSDDs, which is the frequency special domain decomposition in frequency domain. So for the SSI, we have, again, like the previous method, we have adaptive frequency band, but this time we apply isolation forest to choose the most stable pole. Actually, isolation forest is much better than GMM in my eyes due to some differences which are, they directly detect anomalies without assuming any distribution this time. Previously we had it. And then it's much robust to outliers, and it also actually works better with low data. After determining the most stable pole and the successive band, we calculated before the PSD of this frequency domain. We automatically considered that successful band for choosing the stable pole, the peak of the PSD here. How we did this, we used prominence-based peak detection here to automatically choose the peak of the frequency domain. And this is the result for frequency and time domain, as you can see. So I think this is a better visualization aspect in comparison to the previous, just solely relying on time domain. Here we have frequency and time, and actually here you can see the modal assurance criterion, the rate of similarity between 2 mode shapes, which is very important for us to be sure that these are the real modes. And this module also actually provide with the desired PSD resolution by the user, and also the method for actually estimating the PSD. And this is the result of the pole selection. Yeah.
What are those jumps in the animal?
I don't see it. Where?
For example, this one.
No, these are the actually position of the sensor, because they were close to each other. We just plotting them just in a real case, something like that.
For example, the very bottom one.
Here?
There are a few jumps, aren't there? No, it's because of the position.
Yeah, it's because of the position. They were too close to each other. And so let's go for the next one. We use conditional variational autoencoders, conditioned on recording hour and temperature. So here it matters for us if it is like a 10 a.m. healthy behavior or a 10 p.m. healthy behavior. This really matters to us because we are conditioned that. And the other actually important aspect of this method is that it is probabilistic. It's no more deterministic, like creating a determined vector for the Latin space when we were using AE. What we do is, to wrap it up, we find the natural frequency and their corresponding temperature and an hour of recording. Then what we do is we try to condition them with their temperature and hour. And also in sampling here, we also use them because we're using conditional variational autoencoders. And then we reconstruct just the natural frequencies. So this means that we are explicitly using the external factors. And what matters to us, of course, is the MAE or any actually sign of damage. And for thresholding here, we use Gaussian intersection methods. We considered each of the damage reconstruction errors as a set of actually distribution. And then finding the border between the distribution will show us the border, the threshold that we define to separate the health of the structure into warning, alert, and critical. And as you can see here, you can see that this GUI allows you to put natural frequency from first to sixth, and also put the temperature here, and also put the time of the recording. So it automatically incorporates this external effect into your results. Why it matters? Because in the end, afterward, you can also add like humidity. You can add other external features which has their own effect to the results. And as I mentioned, unlike the previous framework, here we have a secondary filter, which after acquiring all of the data, we applied singular spectral analysis here to actually extract the content of the signals, which are representative of, for example, the first dominant component of the structure, or the first and second is up to you. But we chose first here to actually escape from noises here. It is non-parametric in comparison to DWT. It's much easier because there you have to define the types of wavelet transform and then the number of decomposition layers. And then afterward, again, we apply a sliding windowing technique here to like reduce the number of data and then reduce actually outliers. And then we reconstruct a matrix, 10 matrix for 10 sensors. So each sensor has its own actually set of values. But this is X, this is Y, and this is Z. So in three direction, it encapsulates. And then we develop. Then we try to train 10 different one-class support vector machine for each of the sensors. So we consider each of the sensor as a point in a three-dimensional. Actually, sorry, not each sensor, each value of the sensor, each windowed average value of the sensor. So in the end, if we apply a one-class SVM for the new data, we can repeat the same thing and we can see if it is an outlier or not, if it is outside of this border, of this healthy border. So we have a second verification of damage beside the natural frequencies. And then afterward, after we are sure that this is a damage, we plot it in 3D and then we calculate the closest distance, the average of the, sorry, this is the closest distance of the points of the healthy and damage, and that shows the discrepancy of each sensor. And in the end, you can calculate again the discrepancy of the two adjacent sensors and find the zone-based damage. Which I think if I show this is more obvious if I show it here. This is, imagine that in the second module we misunderstood the condition by damage. So we said that this is damage, but it's not. Sometimes it happens because natural frequency actually is not very solid for finding very minor damages. And then here it shows that no, this is healthy, and it shows the cluster of healthy like this. But if it finds an outlier here, it shows something like this. So it will plot your healthy points versus the damage. And it find the distance for each sensor. So you can see, you can set it for all 10 sensors. And then it plots with an accumulative bar here, the localization, which is actually you can precisely localize for all three damage scenario that we have. And for testing this module, we recorded 500 different, with just like the previous setup. And these are actually the natural frequency estimated for the 500 different tests. This was a violin plot of that, so you can see the mean and max and where the natural frequencies are more concentrated. And this is the result for the health classification of the natural frequencies. So different scenarios, as you can see, even the damage scenario has different like time of the recording and temperature, but it was successful in actually classifying with the global MAPE here for all three health classification, actually, all three damage scenarios. And this is for damage localization. After that, the subtraction of two adjacent sensors will show the zone-based damage value index here. And then, as you can see, that for all the three, it was successful in finding the localization. And it's really important because this is an X direction of the structure. And because we had reduction in bolt torque value here, we have to see the damage more in X direction because that is a more affected direction. As you can see here, it is shown that the X direction has a more, and also it shows Y, for example, here has. And this is the cluster of the, as I mentioned, we can do the one class SVM. These are the points of the healthiest structure for sensor number 1 and 6, 1 to 6. And as you can see, they're like actually, in an engineering perspective, they're like creating a specific pattern for each behavior. But this behavior is integrated with numerous factors, which here we considered like temperature and operational. For ongoing future work, we try to do these three things. First, we try to implement it on a full scale structure. I think we will do it next month. And we will increase the number of sensor types. So we have a hybrid sensing system. So we can actually add like strain gauges and others. And then we try to, it would be very nice if we can apply transfer learning so that if it learns the behavior, for example, on this structure, we can like freeze the encoding process and then train it, tune it with for other structures, something like that. Thank you so much for all of your attention. I think I spoke too much. Thank you. If there is any question, I'm so glad to. Yes.
I think it was maybe slide 29. I'm not
Yes,
sure,
exactly.
but it was when you mentioned that I think that recording the temperature at a certain time
Yes.
and recording.
This is 28.
I don't
Oh, this is 26. Okay, sorry.
20.
I just want to have it so that.
Yeah, exactly. Like you,
Okay.
for the conditional
Yes.
a variational encoder, you said that learning that healthy at 10 a.m. is different from healthy at. I'm not from the so I
Sorry, I didn't get what you mean.
like you mentioned here that
Okay.
for the conditional
Variational.
yeah learns that healthy at 10 a.m. is different from healthy at 10.
No, okay.
Yeah, why does it matter the time? Is it just
Sorry.
the temperature that changes or what?
Yes, I will say that. Previously on the AE like autoencoder, simple autoencoder, we will implicitly encode the behavior. So we never say that this temperature with this hour of recording produced this reconstruction error, right?
Yeah.
But this time inside the model, it's like explicitly incorporate the effect of temperature. So for the model, it now matters. When is the recording?
So it's for the model, but
Exactly.
physically speaking.
Physically, there are relations which we never know actually.
Okay.
There's a distribution because for variational autoencoder there is no latency it is a distribution inside. So now it matters like this, yeah. But
Okay, so it's that.
maybe I said it wrong. Yeah. Maybe I confused you. Yeah.
So on this one, because you're looking up to 6 modes, but like the first 6 natural frequencies.
Yes.
Did you do any sort of architecture testing? Because if you go up to a lot more frequencies, the relative sort of dimensionality of your frequencies compared to your heterogeneous or exogenous variables, the ratio will get a lot larger. Do you know if that will be a problem at all?
Well, actually, I think through the modal contribution, it should be enough to analyze the first 4 mode shapes, first four natural frequencies most of the time, because most of the time through the third mode, the contribution is 95%. So you're more or less like actually taking into account most of the dynamic behaviors. But I think 6 is already enough, and it could be also 5.
I mean, it depends on the structure. For civil structures, yes.
Yeah, if we were, but here we are working on bridge structure, which more or less.
Yeah,
but your point is completely rational.
Yeah,
if we work on a very small structure and we have like. Completely rational.
So,
yes.
Like junctions, like
Yes. We can understand it.
highway junctions,
Yeah.
then you need a lot higher, you need a lot more frequencies to be
Of
able to
course.
identify this damage. But yeah, no, I was more just curious if you did or if you're interested in looking at the sort of architecture requirements when
That's
you
a good
have this
point.
ratio of these things. I don't know whether that's something you've looked into at all or
Thank you for the comment.
yeah, no. Any other questions?
I have a question
Yes.
about the wireless sensor. So
Yes, yes.
I wonder what is the ratio of data loss for this wireless sensor? Because I used the wireless sensor before in a real project. The main problem is the synchronization is not the key problem.
Yeah.
The key problem is like maybe in 1 second, if this in 1 minute, maybe there will be 2 seconds of data is lost, gone.
Really.
Yeah, so you don't receive it.
But from the very first moment that I was working with this monitoring system, we actually never faced that loss of data. Actually, it's not my area of expertise because they're also working on the very specific things. But to me, it never happens actually. It sometimes happens that they start later, so we try to like modify the algorithm to synchronize better. But it never happens to me like we lost like 3 seconds. Yeah,
So
hopefully, maybe we were lucky enough to
the
know.
architecture of this wireless sensor network is centralized or decentralized?
Actually, I
Yeah.
don't know.
Oh, okay.
Yeah,
Okay.
yeah, it's not actually my part, but I can just assure that up to now it never happened, but maybe, yeah, that's the point.
Okay. Thank you.
You're welcome.
If there's any more questions in the room or online, then we'll thank you.
Thank you.
Okay.
Thank you so much.
So I had a question, if I may. Sorry. Do you hear me?
Yes, I also I'm turning on the camera. I don't know why.
Okay.
Okay,
Maybe I
okay,
can-
go on, please, Hassan.
All right. First of all, thank you very much for the very nice slides, very nice visuals. It was amazing. I had a question just to make sure that I understand everything perfectly. So the idea basically is that you have some operational conditions like temperature, humidity, and then you want to incorporate this in your model, which is a autoencoder, as I understand. So this autoencoder is basically trained on experimental data. So you measure and then you train this autoencoder, and then use this to give you the healthy response, and then you compare it with your measurements, right? Then my
Yes.
question is that if the operational conditions are changing, like temperature, then do you need to have a time series of healthy data for, let's say, if it's like a bridge for an entire year, because then you need to have measurements in winter, you need to have measurements in summer, in springs, maybe the humidity is changing. So is it really the case that you really need a full year of measurements, maybe?
Actually, you mentioned a very interesting part of it. We on the paper we also mentioned this as one of the limitations. Actually, if the if the external condition drastically changes and it's not in the bounds of the recorded data, it makes lots of challenges. One thing is we have to cover the expected behavior. Actually, Hassan, this is very important for us. So whatever the data set is bigger, is better for us. And the second thing is is the model tuning. In the end, if there are new data, we can like modify the model, something like this. But this is one of the limitations, which it shouldn't be much far. For example, we have now the variation between 15 to 50 temperature. If something happens like minus 20 here, of course, this is a challenge. But for operational effect, when we record, for example, for a month, the normal traffic is covered, something like this. So for operational, we're not concerned, but for temperature, you're completely correct.
But also just to understand, so is the operational conditions an input to your autoencoder, or no? It's just like a general, let's say,
In the first framework, it wasn't, but in the second one, it is directly and explicitly incorporated into the model.
Okay, so it's an input to your model. All right,
exactly.
And then, yeah, finally, maybe just last question is that you mentioned that you also wanted to look at the strain gauges. And I wanted to ask, do you have any experience with the let's say, wireless strain gauges? I know that the strain gauges are pretty small by itself, and if you want to like make them online, or do you need to put the transmitter there? It's another challenge, but do you have any experience on that?
No, we have never actually implemented strain gauges. The future trend of the work is to actually make it hybrid, and this is for the future work. So we've never actually go for actually using the strain gauges here to see their challenges. But in the end, I think if we need a solid framework, we need to incorporate different types of sensors.
Cool. All right, thank you very much. That was very interesting.
You too.
Cool, we're at the end of the time in this room, so one more time, thank you.
Thank you so much.
Thanks everyone.
Thank you. Yes, and have a good day.